My name is Jean-Christophe. I work at Kitware. And yeah, today I'm going to talk about regression testing. There's a lot of different ways of doing testing in Python. Oh, yeah. And I will just take one approach. And it's like between VI and Emacs, you know, there's like different ways of doing the same thing, but I just go with a simple approach, like get the job done. And then we're gonna like go through Q&A, and that's pretty much. And then at the end, you're gonna try to implement a small test, run the test, thing like that. You have a notebook. That's the number 4. It's named regression testing. If you don't see that, make sure you pull the latest change from the repository. And yeah, why do we do testing first? We do testing to ensure that if the condition, if the environment change, if, for example, you acquire an image and then you have a new phone and then the lens is different, the result may be different. Then if you try to change things in one part of your code and then it impacts, you have a side effect on another part of the code, things are going to be broken, you won't realize it, and then you may publish a paper with wrong data, and that's not what you want. It means when you write your code, the idea is to like write the test at around the same time because things are fresh in your mind. If you come back 2 months later, it's gonna be like a black box, and you won't know what's happening inside. There's a lot of different kind of tests, but there's unit test. It means you have like your function, and then you say, okay, I want to make sure that my function is doing the right things. And then you have integration testing, means you have like a pipeline with multiple modules, and you want to make sure from in and out is doing the right thing. You want to make sure that the outcome of that pipeline is correct, and not just every single module, because interaction between this module can fail, and if you just test single module, you won't see that. On the python.org website, there's a page summarizing how to do testing, the approach, and then there's also I don't have that link here, but there's like the hitchhiker, there's like, oh yeah, you're gonna be the notebook, you have a link with like some nice reference about testing. Okay, and then another thing is continuous integration. What does that mean? You have your source repository where you do your pull request, you integrate, and then before you integrate, for example, you want to run your test on a different platform, on different version of Python. And you don't want to manually each time run the test. You want to have these things automated. If something breaks, if your pull request like breaks something on Python 3.0 and you were working on Python 2.7, you want to get an email and say, hey, maybe you want to fix that, and then you resubmit your pull request. Automatically, the test gonna run again, and then if things are green, you say, okay, now I'm ready to integrate my pull request. And there's some nice platform that allow you to easily couple GitHub and Travis CI. Travis CI provide you with for free, provide you with like a build machine running Linux, and yeah, each time you can configure that. Each time you do a commit or a pull request, you're gonna trigger a build on this machine, and then you're gonna get an email back. It's very convenient and pretty easy to do. And like a small example, we have like this Python project named Girder. But yeah, like this morning, some colleague pushed some pull request, and then the system like just started and set up the environment from scratch, installed the package. A little bit like what we did today with Docker, but in that specific case, we don't have Docker. It's just a virtual machine, and then you specify in like a small configuration file which package you want to install and so on, and what do you want to pip install, etc. And then it set up the environment and run your test. That's very, very convenient. And again, yeah, it's free for open source project. And then when you okay, you have this like build machine with like doing these things for free, great, but then how to visualize the result? And there's like some what you call a dashboard. It's like a grid where you display the result of your test. For example, Python, they use BuildBot. It presents you with like a grid of all the platform and the test result. But then there's also like Jenkins going to provide you with some option. But then there's also something like called C-. And for example, for the CPython itself, we set up like a dashboard to build it, and then you run all the tests. And then if you click, you can see like all the Python tests of the interpreter itself that we build every night continuously. And then if there is a problem, you can click on one of the failing tests and you can get more detail. You can know like on which machine it failed, etc., etc. And then for that other project, we have like Python coverage. It means you write all your Python class, you write your test. You want to make sure that it doesn't mean your code gonna do what you want, but it's gonna tell you, okay, your tests at least are going through a lot of the possible like option in your code. And like for example, if I click here that project, we got 90% coverage, which is pretty decent. And then you can click like on the different module, and let's say like the Girder API, then you get like all the different sub file, and then you can click and say, okay, what's happening here, and then you get the detail. For example, here, that exception case is not covered. In the Python notebook, I won't explain how to set that up because it requires a third-party software named CMake, but if you want to learn more about that, how to set that up for your project, I would be happy to talk to you. Okay, now let's come back to the notebook. It's the number 4. It means here I already opened it. And what we're going to do in the data processing, you use a class named iSize to get the size, the radius of the estimated radius of the size of the eye of the tardigrade. And what we're going to do, we're going to add a small test to make sure that for our image, we get the expected result. It means we know that for like one kind of data, we get, let's say we get a result of 85. And if something in the code, like let's say the filter we use to extract the information change, if you update the version of simple ITK, and you don't get 85 anymore, it means something is going on, and you need to look at it, and you're going to be notified by your continuous integration or thing like that. But the first step is to write that small test. It's like few lines, and before we write the test, we need to identify what are the input of the test. It means in that specific case, we got the image, the input image, and then we got the seed point, and the output going to be the segmented eye and the estimated eye radius. And for that small test, we're going to just focus on making sure the radius is correct. Okay, a first draft of that test will be download data from Figshare, given the ID. Oops. Then save to disk with a name, read the image, run the filter to estimate, and then get the radius, and then you can like compare things. It means here I'm gonna just run the code. Here I just change the folder. I go index test, and now what I'm gonna do, I'm gonna display and run the test. Yes. And if you do the same thing, you're going to be able to see a small pager down there that show you the content of that small test that we implemented. And is there a way to, yeah, excellent. And here it's just a simple function named iSize basic test. And here what we do, we download the image using our downloader. We read the image, call the estimate function, And then what we do here, we do an assert where we check that it's the expected value. And if the assert fails, we're gonna have an exception, and then I mean you're gonna know about it. We could also return false or true, but for the coming step, we're gonna use like some convenient tool to automatically run this test, and they are exception based. That's why we are using assert. Okay, now let's come back to the test. Now, if you uploaded, yeah, as I mentioned earlier, yeah, if you don't see the notebook, make sure you update your checkout because we integrated this change this morning. And if you prepare like a few days ago, you won't have the change. It means if you just do a git pull, it's gonna work as explained earlier. Does everybody got the notebook? Or if somebody doesn't have the notebook, raise your hand. No. Oops. Okay. It means if you uploaded data on Figshare or like any other sharing site, you could adapt the test to grab the data from there, or you could just change the Figshare ID to match the one you got when you uploaded your data, and then you can rerun the test, and basically you can just do Control-Enter, and then since the input is different, I will expect the radius to be different, and then you're gonna get an assert, and then you're gonna adjust that to change the expected value to what you have, and then you're gonna have your code gonna run with your data, and then if you update something on your machine and the filter is broken or something is wrong, the test is gonna fail, and then you're gonna have to fix something. Sometimes when we update library too, we got a different result for this like expected value. It's because if, for example, we optimize a framework, a registration framework, or some filter with if it improves the numerical accuracy, you're gonna have like a slight difference. It means when you have like this expected result, you could do like fuzzy compare and be more smart about things. But in that specific case, you just do a basic comparison. Okay, what can we improve here? If you look at that test, in case of failure, we don't really know what's going on. We don't really know what were the input data. We don't know what was, at least we don't know what is the current value, and we don't know what's the expected value. It means we need to make that things a little bit more verbose. And yeah, when you write test, make sure to add enough information in case of failure. Because when you write the test, everything works fine, and okay, you see nothing, but then like 2 months later, you're gonna have a test that failed, and you're gonna be like, oh, what's going on? And if you add enough information, name of the input image, the ID, and then all this, they're gonna give you good hints about what's going on. And usually don't output information if things works well. If it works well, the test's gonna run, you won't pay attention to it, and you're gonna be extra noise. It means you want to display information in case of failure. I mean, you want to display which test is currently running, sure, but don't like overdo it. Yeah, you don't want to pollute the output. Now I have another version of my test where I display information in case of failure, and then if you look here, I change the assert, and you can just add a comma, and then you can add a message that's going to be printed in case if the assert is not validated. You're going to get that message, and then here you're gonna display problem with estimating radius, current, then you display the value, and then expected, and then it give you more information about what's going on. Then what else? Here we download data and we create an output, and The problem with that is that when you're going to run the test again, you don't start clean. You have data there. And in that specific example, okay, maybe it doesn't matter, but it could matter, because let's say the download fail and you still have the previous image. Your code going to run with the previous image, and then that's going to give you false indication. If you don't delete that file, the test can pass for like, with the download that fail, can pass for like, can succeed for months and you won't realize it. It won't be a big deal in that specific case, but yeah, it might tell you that, yeah, maybe the download, you don't know then if the downloader is doing the right job too, because the image is still there, and maybe fixture API change, and then you're screwed. Means start with a clean plate and make sure when you start your test, you clean things, and you can keep things at the end, then if you want to go check, you're good. But when you start, make sure you start clean. And what we're going to do here, the downloaded image, we're going to just put them in an inputs folder to organize things a little bit. And then we're going to write the output in the outputs folder. It means what we need to do first, we need to delete the current image to clean things a little bit. And then, yeah, if we do ls, we're going to see the content. No, I can't do that. Maybe like that. Yeah. Maybe another cell. I don't know. Oh, I should do probably. Yeah. And yeah, here I can't delete the image because I already did it. And I see that I just have my Python file. I don't have any data here. Good. There's another file named iSize2 clean plate where we implemented, we just updated the code to deal with this like input folder. And yeah, what you're gonna do here, we just create an input dir, output dir, and then we create the image path using that. And then we also clear the input folder if it exists. Python provides you with convenient function to do that. And we clear the output folder, and then we start to download, and we do the same thing again. Okay, then next, what else? We can see here that the name of our input and output is like very generic, and it's a good practice to put some context in the name of your input and output. And in that specific case, what will be this information? It will be the name of the input image should include the fixture ID. That way, if you go check what's going on you SSH onto your machine or like you build machine and you're like, oh, which image, what's the ID, and you share that with a colleague, the image carry that information, and then you reduce confusion, you reduce problem. You don't have to say, hey, by the way, that's the ID. The information is embedded in the name. Same thing for the output. You can add the coordinate of the seed point. And when you have like more complex pipeline, that's pretty convenient. And it allows you to do, when you do, I like that small website. It's named short, self-contained, correct, compilable, parenthesis, an example. It explains like often when people have issue, they just send you like a link to their big application. It's hard to know what's going on. That things remind them to do some work beforehand and trim things. Okay, let's close the parenthesis. But yeah, having like meaningful name is helpful in that case. And how does that look? Now I have my file, and what I'm gonna do here, I'm just gonna bring everything up in the file and my fixture ID, seed point, etc., and then I create my name using this information. And yeah, now if you just display the content of the input folder, we got our image. The output folder, we got output. Okay, now what else? okay, great, we can run a test, but you want to automate things a little bit. And how do you do that? You're going to use a test driver. There's a lot of options, PyTest, Nose, unit test 2, and so on. For that example, I'm just going to use Nose. It's already available in Docker. If not, in your Python installation in Docker. Otherwise, you can just do pip install Nose, and you're going to grab it for you. And what's nice is that Nose, you come with a small convenient script, and then you, by default, you run in the current folder, and you're going to inspect all the file, and if there is function that start with or end with test, you're gonna run this function. And if the file also end with test, and that way you can very easily execute your test. And what we're gonna do here, I'm gonna just try it here. And since we have this like 4 version of the test, they are all valid version, but we improved them, and I'm gonna just rerun that, and here I expect my 4 tests to pass. And here it's downloading the image, and you can see that the kernel is busy. Okay. No, that's great. What we do in that small function, we download and we run the filter, but there's something that we could test independently is the image download, the download function. And what will that test do? It will try to download the file. You've got how do you make sure you got the right file? You compute the MD5 sum, and what your test could do is download the file, read the content, and compute the MD5 sum using Python, and you provide the expected MD5 sum. Then you run that small function, and if you have an issue, you're gonna know that. Yeah. I covered everything. Is there any question?
So I noticed that, so it looks like you have separate Python scripts with each test and then a function inside that script. Is that pretty standard to do it that way, or to put it in have one testing script that has?
What I will do in that case, there's a class named iSize, and I will create a unit test. I will create another class that derives from unit test, and then I'm gonna add one function. But I'm gonna test each function of my class. I'm gonna have like test underscore set image, test underscore set radius, and test underscore estimate, and then I'm gonna be able to test my class. For sake of simplicity, we just use that approach, but yeah, you should adapt that to what you have in the structure, and but yeah. Yeah.
Comparing to some value. And so you could write like a simulated eye image or something. Are you aware of research projects that, like maybe real published research, where they've tried to cope with that challenge and write tests on real scientific data?
Let's say you do medical imaging, image processing, and who is saying what's the ground truth? It's the doctor and the researcher. You work with this guy, and they say, okay, what you get at that point in time is the ground truth, and it's what we think is good. It means in your test, you say, okay, that's what I expect, and then you can start with that. And also, when you start to develop your algorithm, you're gonna create some you're gonna simulate some data, and you can also include that in your test data.
So usually both would be used.
Yeah, and often what you do too is that you, like if you do medical image processing, you have this like giant data, and what you're gonna do, you're gonna create some you're gonna subsample them, create some smaller one or some, and then your test gonna run faster. But you still want this like long test that you're gonna run once a week, because that's the real data that people are gonna use. But yeah.
Do you want to mention the grand challenges kind of exercises where data with ground truth is made available?
Oh yeah. What's happening too is that for this like scientific problem where people want to develop like a better algorithm, there's like this Grand Challenge website where what's happening is they say, okay, that's the ground truth. That's what we think is good, and that's the input. and write some code that's going to get us close to that. And then they compute some metric to say, okay, how good is your code? And it can be open source, I mean, depending on the setup, but it can be like open source code or closed source. And then you're going to have some company who are going to say, okay, we are also participating. But at the end, you're going to see that the open source, where you see what's going on, gonna win.
Something that is interesting in the grand challenges is that you started splitting the notion that a single researcher should own the entire pipeline, from data acquisition, data sharing, processing, analysis to the end. That is part of the problem of reproducibility, is that we have that pipeline. And for your professional career, you only get credit when you do the entire thing. So there's a tendency now to cut that in pieces. And if you're just acquiring data, you are making a valuable contribution to the research community. And you should get your promotions and your tenure and your raises based on that. So, for example, what we did with Figshare is a way of building a career out of sharing data and getting references to it. So the grand challenges is going into that more horizontal partition of tasks. Somebody acquired data that is really good. Somebody annotate this data and say, this is a tumor, and this is how big this tumor is, and make this available so anybody who is developing algorithms for recognizing tumors can go to this data and use it as a benchmark. And then you can compare apples to apples, as opposed to what happens very often in papers where you publish a paper with particular data and an algorithm, and I publish another one with different data and another algorithm, and try to say that mine is better than yours. But we don't have a base comparison. So that's part of what challenges are doing. Now, when you have tools that provide, like ITK or simple ITK, provide you with algorithms that are standard, then you have the standardization in the other axis. So same code, different data. Or same data, different codes. So that's part of that process. And the effort in reproducibility is to make sure that each one of those activities are described precisely enough that anybody else can redo it again. And then we can actually compare.
Thanks. Any other question? Okay, now I'm going to talk about literate programming.
Okay, so everyone's learned how really easy and simple it is to do reproducible research, right? It's just piece of cake, walk in the park. Okay, it's still a challenge. As well as our tools have advanced, it's still a challenge. And our goal here is to minimize the challenge, and especially to minimize the unnecessary challenge. And so what I want to talk about here is actually getting to a finished paper or a finished research output that can be published and shared. And the idea here is that we want to we want to be able to publish a paper and then back it up and say, okay, here's our PDF. How did we get from our research to this actual printable thing, and how do we get there? We want to do that because we want someone else to not have to spend time figuring out what they think we mean in our verbal description. We want to be able to say, yes, my results are correct. It's going to take you about 5 minutes to check. We saw the Rogoff example of the Excel spreadsheet gone wrong, and of course the other famous example of the spreadsheet gone wrong is with Piketty's book about capital. And I've looked at the spreadsheets for that, and I do plan to use DEXI to generate some reproducible versions of those, but just the workflow involved in the work involved in determining if those spreadsheets are correct is minimum a lot of hours. It's not a case of reading a script and seeing if the script is valid. It's a case of going through and recreating every single cell. So what we want to do is to minimize the amount of time that it's going to take someone else to determine how you got from your results to your paper. And it's actually, I think the more important thing is not the amount of time that takes, but the uncertainty around the amount of time that takes. And if you, if you have a GitHub repository, if you have a version control repository on GitHub or elsewhere, and if you see in that repository that there is a Docker file and that there is a dexi.yaml file, if you either will know in 5 minutes, you should know in 5 minutes if that's going to work or not. And if it does work, you should be done with reproducibility, because what we have is a Docker file that is going to create an environment with all the necessary software installed, and then a DEXI file which is going to, within that environment, perform all your calculations and generate your finished paper. So with those two ingredients, someone who has the software installed should be able to recreate your paper. And if they don't, they should know exactly why, because they'll get a very specific error message, which is a very, very different situation from, okay, here's my paper, here's my repository, good luck trying to figure out what I had installed, good luck trying to figure out the order in which to run all my scripts, good luck trying to figure out how I actually got those into my paper, because actually I copied and pasted from a bunch of different manual runs. So a really good rule of thumb is anything interactive. The more interactive something is, the less reproducible it is. And the more automated something is, the more reproducible it is. And what you really want with someone else is to be able to hand them a box with a big button on top. And the box is your GitHub repository. And the big button is going to be a single command, or as close to a single command as you can get, that's going to reproduce the final results. And we're getting really, really close to having that single push button command with the combination of Docker and DEXI, for example.
So are you going to go into what DEXI is?
Yeah, sure. So DEXI is, basically DEXI is a command line automation tool which runs whatever scripts you need to run, and then it will insert content from the generated scripts or from the source of those scripts and put it into a finished document. So it is, one way to think of it is a document-oriented make tool. So if you're familiar with make, it's going to be a way of automating a bunch of tasks in a particular order. The difference is that it's going to be a lot more focused on documents and the things we need to do for documents. Okay, so we're in... Okay, so there is in the notebooks directory within the example, we have a directory called DEXI. And, okay, is that big enough to read? More or less, okay. So this is how we configure DEXI. This is a YAML configuration file. And what we're doing is taking all the elements. Oops, okay. So what we're going to do is take a lot of individual elements, all of which are basically the standard elements that you can see in a repository. So we have our Python script, and this is just a normal Python script that you can execute. And what we've done is take the contents of our IPython notebook that we've done in the exploratory stage of our work, and we've sort of distilled that down to what is needed to generate the images we want to include in a paper. So we have, we've got our Figshare ID, we're getting the image, we're downloading it and saving it locally. And one really important thing that DEXI does, if you were just to execute this Python script locally by just running python00.py in this directory, you would get a JPEG file in the local directory that contained this information. And as was pointed out in the previous session, it's possible that that is going to linger between runs, and it's possible that that's going to get out of date and out of sync. And so one really important thing DEXI gives you is a really lightweight degree of isolation by running all these scripts in working directories that are very specific to that task. So what's going to happen is every time you run DEXI, if the file system, if the inputs have been modified, you're going to get a new working directory. It's going to execute this script in an isolated environment. And so you can just use local file names, and you don't have to worry about giving them crazy names to differentiate between different things. So when DEXI is going to run this script, it's going to do the download for us and save it locally. But we know that every single time this runs from scratch, it's going to redo that download. We're not going to get stuck with stale things in a cache. And then what we do, we calculate the estimates. We do our image overlay. We're saving everything to local files. And then finally what we're doing is we're saving our radius estimate to a text file. And what we're going to do in our report is we're going to actually read that result from a text file. So instead of calculating the result and copying and pasting it or manually inserting it into your document. We're going to save it to a JSON file because that happens to be a particularly convenient way of saving things. And then we're going to load this directly into our document. And the advantage of doing this is, first of all, it's very transparent. We can see where the piece of information comes from. And secondly, if we get a new image, let's say we get a new image and we want to recreate our results, or if somebody else wants to go through and substitute a new image, the number that appears in our paper is going to be the up-to-date number that appears. It's not hard-coded. It's not manually inserted. It's going to be based on the last run. Okay, so this is our document. It's a LaTeX document, and for the most part, it's a straightforward LaTeX document. But what we have in places are special syntax codes, which are for the Jinja templating system. And this basically says, hey, insert some dynamic content here. And what DEXI is doing is preparing the dynamic content behind the scenes. So when you come to write your document, all you need to do is say, hey, I want this information at this location. So we're putting in some nice syntax highlighting. Then down here, we're just writing normal LaTeX. And DEXI is not LaTeX specific. You can write any text-based format. So for example, you could write in Markdown or restructured text or any of those. ASCII doc is a really nice one. And DEXI will be able to convert that for you. So with DEXI, you design a pipeline. Usually you're going to do your templating first, and then the last step is going to be to render your document to whatever final format you want. So DEXI will handle running LaTeX for you. It'll handle running BibTeX for you. It'll handle converting Markdown to HTML or whatever else you want it to do. Yeah. Yeah. Okay, so here we have our document. We're running through. This is just normal stuff. Okay, so here's the include graphics. And if you remember, this is the name of the JPEG file that we saved in our previous script. And all we have to do is use the local name. And once we've specified our dependencies correctly, DEXI will place that file in the correct directory, so LaTeX will pick it up. So the thing here is that you don't have to do a bunch of fanciness to carefully cache your images and make sure you've got the right one from the right batch. DEXI takes care of that for you. You just have to save stuff with the correct local path within your project. So basically, that JPEG does not exist in the repository, but it will exist at the time your document is compiled. There's another image. Okay, and now, so here's another image generated in our PNG, in our Python. And what we're doing here is we want to now actually, as well as showing the generated image from our script, we'd like to document the code that got us that image. We want to say, hey, here's the specific implementation we did to get this image. And we don't want to copy and paste the code from our Python script into our document for the same reasons we mentioned before. What if it changes? Also, copying and pasting, that's extra work you have to do. So what we want to do instead is make a reference to the location within our source script of where the relevant code is. And that's what this little thing here does. So what we're saying is that here's our source file is 00.py. We've done some things to it, which are applying DEXI filters. And we'd like the section called segmented that appears out of there. And here is the section called segmented. So we define a section by using just 3 comment characters and a section name. And so you can see that what we're showing is really just the relevant parts of the code. And we don't need to show all the setup code because that's not going to be helpful. But it's in a repository. If someone wants to see the whole script, they can see it. But we're just going to choose to show the stuff that's specifically relevant to how we did this implementation. And then finally, we want to say, okay, now the point of this was to calculate, the main calculation we wanted to do as well as generating the images was estimating the radius of the eye. And we saved that to a JSON file at the end of our script. And so what we can do here is load the name of that JSON file. Again, this is a JSON file that doesn't exist at the start, but it will be generated by our script during the run. We're going to load that in. And because of a combination of DEXI's magic and Jinja's magic, we can actually just call the .radius accessor on that. And that's going to convert the JSON to a dictionary, and it's going to pull out the element in the dictionary named radius. And that's where we stored the value from our script. Okay. And again, here's another part of our document where we're actually describing how we did the overlay. So so basically what we have here are a bunch of elements, and the configuration file is going to describe how those elements depend on each other and what DEXI needs to do to process that and to generate our final result. So the .py through the Python filter, this is saying to actually execute all the Python scripts. So this is saying, if you find something with a .py extension, we'd like to run that through the filter that's going to evaluate that in Python. That's also going to generate a lot of files as side effects, and we're going to tell DEXI, okay, for the Python filter, we'd like to add all the new files you find, which are side effects of running the script. We'd like to actually add those, keep track of those. You don't necessarily always want any new file to be generated. Like if you're running LaTeX and there's a bunch of .log and .ox files, you don't care about those. But if you're running a Python script which generates a bunch of JPEGs, well, those are ones that you want. So in this case, we're going to say, hey, pay attention to these new files, capture them, make them available. And because so the Python file is indented under our LaTeX file, and that means it's a dependency. So that means a couple of things. It means that DEXI will know that it needs to run the Python script first. It's going to do this in the correct order, because if you go to write your document and the script hasn't been run yet, you won't have all the nice data available. And it's also going to make all those resources available to the LaTeX document when it renders. So the LaTeX, one thing DEXI does is it does not make everything available to everything else by default. So when you run a script, it's going to, if you don't specify dependencies, that script is just going to be on its own in its temporary working directory. There's not going to be anything else there. And so what you do to make them available is specify dependencies, and then that ensures things get run in the correct order, and whatever you've told it to be available is going to be available, and whatever you haven't is not. So for our LaTeX document, we're going to take our LaTeX document and run it through two filters. The first filter is Jinja, which is the templating system, and Jinja is the thing that's going to fill in all the blanks. So all those tags we put in referencing locations of other files, Jinja is going to go in and fill that in with the appropriate content. And in this case, a lot of them are Python source code, which is going to be syntax highlighted. And this line says, take the Python source code, separate it into sections, apply syntax highlighting, and hey, make sure it's LaTeX syntax highlighting, because the default's HTML, but we want LaTeX codes in there. Okay. Okay, so, and do we have Savannah here? Okay. Yeah. Very cool. Thanks. Okay, so this is the entire build and run script, and it's going to go ahead and run the IPython container, but the important thing is that what it did first was run the DEXI container. Okay, that's fine. Okay, so what we can see is that there's now an output directory in the DEXI container. So I just ran the build and run script, which we've hopefully you've seen that a lot. And the build and run script builds each of our different images. One of those images was the DEXI image. And then it actually runs the DEXI command. Okay, so the image in a totally automated standalone way, the Docker file with DEXI takes the main Docker file as its base, and then the DEXI Docker file, its only job is to run the DEXI command within that Docker file. So we run it, we mount our working directory in there, we run the DEXI command, and we exit. And because we've mounted our directory, it's actually going to write the output we want to the output directory. So what we can see now is that we have, what's the PDF viewer? Is it on here? Do we have a PDF viewer? Command line? It's not on there. Well, I'll try it. Maybe it's just not auto-correcting.
Yeah, but
Okay, so is there, okay.
Yeah, that would be the viewer.
Okay. All right, so will that work, or will it, if you don't have X windows, then that's probably a lot of stuff. Is there?
It will not open anything.
Okay. Is there another way to open it from the browser, maybe, or what do you think?
Yeah, we put it in the public directory.
If you do Firefox on the PDF, will it open? Or just go to Firefox?
Use SciPy. Is it some?
Output. And then sandhopper.pdf. PDER.
Sorry.
Thank you. Okay. Wonderful. So Linux is great for reproducibility and not so great for actually GUI type things. Okay, so this is the generated PDF that we've built. So what we've got is obviously all the content we put in here, but we also have the image, which was the one that was actually fetched by our script, and we have the modified image, which is the one that was actually processed by our script. And then we have documentation of the code we used to generate that image. And you saw the source where we did not hard code this. We just referenced the section in the script. And here's more. And the value of the radius was 85. So I'm going to quickly tempt fate in this. Okay, so what I'm going to do, and I'm not sure if this is going to work, is add a comment so you can see that we're changing the source code. Oh. Good. Okay. Okay, so that's not going to work because it's Did that run? Okay. Okay, maybe that did work. Okay, so that did work miraculously. And what we've got here is we've changed the source code in the source file. We reran DEXI, and now we can see the source code updated in our PDF document. So what we have is a PDF document where we have not hard-coded any of the information. We can go back and edit and tweak our code and just rerun DEXI. So DEXI is going to give you a pile of static documents. It's going to give you a perfectly normal PDF or a perfectly normal HTML file or collection of HTML files. There is nothing special about them. They are just normal static files that you can upload or submit or do whatever you want to them. But what's wonderful about them is you can regenerate them from their sources at any point in time. And hopefully someone else will be able to regenerate from sources at any point in time also, assuming you've got a fully self-contained and reproducible workflow established in this. So one nice thing about Docker and DEXI together, Docker gives you a reproducible environment, and it also gives you an isolated environment. So it's very good at enforcing that discipline of making sure that you really have captured everything in an automated way. It's really, really easy when you're working in your local file system to reference a local file in some other directory that's not part of your GitHub repository, or to reference something in a way that's not going to be valid on someone else's machine. So one thing Docker gives you is it sort of forces forces you to use a really restricted environment, and that's good because that's what other people are going to have to use. So it's really one of the big barriers to reproducibility is you don't remember everything that's installed on your machine. You don't remember everything that's part of your workflow. And when you start working in a Docker environment, you start with a very, very blank container that has nothing in it. If you look at our Docker file, you're seeing that we're installing really, really basic things. And it might seem kind of silly to go to that extra work of installing all these basic things that you have on your laptop. But what that gives you is it makes sure you have a minimal environment, because there's no point telling people that they need to go and download this huge thing that happens to be installed on your computer when it's not relevant to the actual computations you're doing. So with Docker and DEXI, it's a lot of reproducibility is about discipline of truly automating your project and not taking the little shortcuts that are really, really easy to take, like referencing something that starts with /home/me/ oh, it's there, I know it's there. Oh, sorry, that's right, of course, you're not going to have that. So one nice thing about, we're using Figshare to upload because that URL should work for everybody. If, we've set it to public, it's hopefully not going to go anywhere. That URL should work for everybody. If that's the basis of our script, then anyone else should be able to run that script and we should be able to get the reproducibility. So once you have this workflow up and running, I know it seems like a lot of work right now and it seems kind of frustrating when it doesn't go the way you want it to, but once you have Docker set up and once someone's project has a Docker file and a DEXI file and a bash script to get everything just running, then that bash script that launches Docker and runs DEXI in Docker, that's our one-button, push-button reproducibility. And that's the standard that, in order to make it realistic for other people to do the computational reproducibility, it has to be as close to one button as possible for all the parts of your workflow where that makes sense. And obviously, as we saw today, things like taking a photograph of a tardigrade, that's not something we can automate in the sense of, we don't have a robot that we can give instructions to actually do that, at least, not yet or not in this context. But for where you can automate to the point that it is completely one button, push button, get everything, that reduces the burden of work on other people trying to reproduce. And it also reduces the burden of work on you when you go on vacation for a couple weeks and can't remember what you were doing when you went back, or if you go to lunch and can't remember how you were running things that morning. So this is not the way we're used to working. And it can seem like a lot of extra work. It can seem like, well, why would I want to go to all that hassle? Why do I want to force myself to have this seems really awkward to have to, include everything and do everything. I just want to, leave my session open and just keep working and copy and paste. But in the long run, I wouldn't dream of working any other way. I don't like to work interactively at all. I like to have everything in a script from day one, and that, probably seems pedantic, but it saves me work in the long run, and it means that I always know exactly, I can always pick up exactly where I am and get things working. So with DEXI, you can incorporate your raw source code if you want to document, here's how we did this little chunk, here's the actual source code. You don't have to include so much source code that it's overwhelming. You can just include the relevant pieces, and then people can go to your source and look for the rest of the information that they need. And you've got the ability to actually include individual values and include them in the text. Like if you're reading the sentence, the value found was 85.0, there's absolutely no, you don't care that was an automatically generated thing. It doesn't look any different than anything else. It's completely integrated into the content. And you can do things like generate data tables. For example, R has a wonderful package called Stargazer that generates really, really pretty LaTeX formatted data tables. So you can use DEXI to, you can write an R script, load your data from, say, a CSV file or whatever other format you've saved it from your Python script, go into R, open that up, generate a nice LaTeX markup for a table, save that, and insert that into your document. And again, all those steps, once they're part of an automated pipeline, it doesn't matter how many extra changes you make because the marginal work to you is, virtually zero once you get everything up and running. Okay, so I'm going to stop there, and please find me over the course. I'm going to hear throughout the entire conference. I'm here through the sprints. I'm actually here a little bit after that. So please come and find me, and please ask me questions, and please ask for help in getting your environment up and running, because I would love to see people have a working setup by the time they leave SciPy. Please ask me for questions, and please feel free to email about DEXI-related questions and help getting started. Once you get an initial setup, DEXI really shines when you're iterating it. So the tricky part is getting your initial document and your initial script and get everything working together. Once you have that set up, then you saw we just went in there, edited a file, added a comment, ran a single command, and got our updated PDF. So again, thanks. Please find me, and we'll go on to the next part of the tutorial. Are you saying like to automate like an entire chunk of something, or?
Just to say, like, I'm finding this research work, and in my mind at least, what I try to think about is what kind of figures I really want at the end, what kind of results, people drive those, then I can sort of go back.
Yeah, I mean, you could do something like a lorem ipsum bunch of figures where you've got maybe a stub Python script or a stub script of whatever you want to use that's saying, okay, I'm going to have something like this here. And then as you go along, you're filling those in with the actual code. I mean, yeah, it's up to, you can certainly write your document. I mean, what you can certainly do is plan out your document and stub out the section headings and stub everything out. And I mean, DEXI can be used just to compile LaTeX to PDF. You can use it just for that. You don't need to do anything fancy. So you can start out with that structure, and then it's very easy once you've got it set up, as you add scripts to it, as you add incremental elements to it, to then incorporate those. So yeah, you certainly could do it that way. I think that would just be a brainstorming of how that fit with your workflow.
I have also a question, like some journals require to upload the text file. So can you actually usually do it with this empty spaces?
What you can do is just run the Jinja filter without running the LaTeX filter, and that'll get you a tech file with all the source code put into it. Yeah, so you just wouldn't go the next step, and then that's going to be something that you can upload to it. You can get the intermediate. Yeah, you don't have to render it. Yeah.
So I was curious, how do you do, like, so I'm working on a paper right now where I have some heavier computation that I run on a supercomputing cluster that I can't really automate with a Docker container for our supercomputing cluster.
Right.
What's the good policy for how to break things? Do I just treat the results from the big supercomputer runs as the
I would say,
data?
yeah, I would say, I mean, yeah, you have to draw a reproducible box around some part of it. And I think the important thing is to have as few moving parts. I think ideally you would have DEXI be able to submit that job through some sort of automated API and wait or check for the response. And talk to me about that offline, because that's something I really want to explore. But yes, taking the results from that run and using that as the input, and then really documenting how you got that result file is a good approach. And one thing, just one little hack around the parts of this that you can't automate. A really good technique for this is it's really easy to think you've documented a process. And a really good hack, if you can't automate something because it's not scriptable, is to write down the instructions and either ideally get someone else to follow your instructions literally, or if you have the discipline, you can do it yourself. Follow your instructions literally. So you're going to have to document the process of submitting that job and where to put the results and how to name it. So what you can do as sort of a next best thing is to actually document. Okay, here's what you do. This is the format, and you do this, and you do this, and you do this, and.
Anybody else trying to reproduce it is likely to have a different supercomputing cluster than I do, which the job submission is going to be.
Right. Okay. So in that case, you just document the format of the results file, and use that as your starting point. Have either commit that as part. I mean, that can just be part of your data committed in your repository or something else. So there's usually a couple different ways to get to the objective. And the thing with, like, if you do backups on your computer, then you know that the important thing is not doing the backups, it's how do you actually do the restore. And it's the same with reproducibility. You're only going to learn how good your reproducibility is when you or someone else tries to start from scratch and reproduce things. And I learned this one the hard way because I thought that my thesis was automated, and it was not automated enough. And that's why I later wrote DEXI. But consuming the reproducibility is a really important part of testing it, and that'll tell you really, really quickly what information is missing and what's difficult, what's hard to do. So iterate your whole process.
Yeah. For like to document protocol, there's a website, it's named protocols.io, has been created by some biologists to clearly document what do you do in the lab, but they want to extend that to any sort of protocol, and it's named protocols.io, and I think it's something that worth monitoring and to see in which direction that's going.
Yeah. And if you did that, then maybe that would be something you automate pulling into your document as an appendix. Like if there's an API, just grab that and stick it in there.
You talked about DEXI as a make replacement, right? I presume for actually driving compilation, you want to chain things, so DEXI drives some sort of CPAC or something.
DEXI drives, yeah. I mean, if it's not it's optimized for automating documents and projects. It's not optimized for compiling. So yeah, you would automate. You would get DEXI to call whatever other thing you actually are going to use to do the compilation. Yeah.
Great. So thank you, Anna. So let's take 10 minutes maybe and try to generate that PDF locally. So if this, right, so we have this build and run. If you didn't get Docker working, and I know a lot of people didn't get it working, the commands basically are to go into the repository, into this DEXI directory. So we're not in the DEXI directory. In the notebooks/DEXI directory. Okay. And if that build and run script doesn't work for you to run Docker and have Docker run DEXI for you, the equivalent is if you're using a local DEXI install, it's DEXI setup. First time through, you have to run DEXI setup once at least. And then every time you want to rerun the analysis, you make a change in the script, you make a change in the documents, you run DEXI, which is the equivalent of running make. So use Docker if you got it. If you don't, and you install DEXI locally, you can try using that to generate the output. And again, the output is in this output directory. You'll create it in the output directory, the PDF file.
And obviously, when you're running DEXI locally, if you're running it outside of Docker, you're going to have all the software installed that it calls. Otherwise, it's not going to work. So that's LaTeX. That's everything documented in Docker file, but it's LaTeX and simple ITK package and that.
Is there a plan with DEXI? Here we wrote that script, but let's say you don't want to redo all the Docker things. You just want to rebuild your paper to have like more file approach to it, or like?
Okay. So if something is a dependency of something else, you have to run all the dependencies. But you don't. You can run just a particular target, if that's what you're asking. Or also, DEXI caches everything that hasn't changed. So if you're just editing your paper, it won't redo all your calculations unless you change something in your calculations. Is that what you're asking?
It's like here you run the build and run script, and then that thing's run DEXI, but shouldn't be the other way. We start with DEXI, and DEXI is doing the thing.
Right. I haven't built that, but eventually, yeah. I mean, I've got to figure out the best way to have that where DEXI is driving Docker, which is then driving DEXI. So it's a little.
Because otherwise, for more complex system, you have to deal like option to your bash script, and it's gonna be painful to get that.
Yeah, I think bash calling Docker calling DEXI is optimal, but that's in development. So.
Okay.
Cool. So let's just take maybe 5 minutes and try to generate your PDF. And so if you don't have Docker working or you have a hard time installing the dependencies, right? It's a good lesson in the experience that other people are going to have with your own material, getting their own local installs of crazy scripts and analysis, and trying to reproduce your work. Overall, a good lesson to take home. So if you have any questions, please raise your hand, and we'll go around. And next up, we'll take all our results that we've been getting so far, and we'll show how we can publish them in a publication where we're referencing all the data, the source code, all the source code we used, and the actual document itself. So.
Okay, so while we are in the break, what we're going to do next is to take this article that we created and submit it to a reproducible journal. And we are also going to take your repository that was cloned in Docker or the environment that you're using, make a change there in a branch, and push that branch. And the purpose of doing that is to illustrate how collaboration works in that space. So how this new age of scientific collaboration will happen in the open space, in a reproducible environment. So I guess what we need to check is, please do a show of hands if any of you have had trouble with cloning the repository somewhere where you can push a branch. So if you have had trouble creating that clone, please show your hands and we'll help you so we can get you to do the branch and pushing when we get to that session. So anybody has trouble cloning?
Which repository? Just the main tutorial repository?
Yeah, the tutorial repository. We'll use that one. We'll make some small change in a README file, for example, or add a new file and push that up into a branch. So anybody don't have the repository clone?
One quick announcement. So I see a lot of Mac laptops here, and people were confused earlier, like where to run the commands that starts with Docker as the program name. So those has to be running inside your VM. So once you do boot to Docker SSH, you will log into your VM, and then there you run all your Docker commands that we have on the instruction set. So if you have any issues on Mac, let one of us know, and then we'll help you get the system up and running. Thanks. Yeah, you call the repo and then you would
because the other thing is, I noticed that I was using the Docker, and I would read it, and then I would clone the, so I would clone the root out, but then start up the Reproducible, and then go back in. Should it be like if I do it here?
yeah. That means that you are inside only but if I type
So yeah, that's right.
only Docker is there. Is there Docker there? No. Yeah. Okay, so you said. But I thought you said we should packetize by inside to see what he's doing. But you know we are into the container now. Okay, so then three. Wait, three. Yeah. And this is only supposed to be Mac. Mac. I believe it doesn't have the Linux. Also Linux, there's no right now we're doing Linux, it doesn't have a host, but you know, right. If you were Linux, we should have made this bit more clear, but there's lots of things like that. But so what's the middle of /home/Docker? Why is that? Because he's no, this is VM. Oh, okay. Well, he hasn't got the latest software. No, so fill in the entire thing. So this command, like, you know, so you have to like Docker build dash t native style. Yes. What's possible? Get up yourself. We deployed that 20 times a day. It's deployed all over. Yeah, so now what it becomes is then you use the diaphragm design run this thing. Oh, thank you. I was really confused. Does not download the virtual machine. So it's very old, so I couldn't install it.
So I did that from
your other system from
I mean, yeah, I only do the Docker now. It creates a new one, bash thing, and I run it from here. I did see some explanation.
no, I'm just boot it up with this. I think that's just going to get daemon. It doesn't actually change. So when you run all this command, you just run on your own. So boot up is the so when you run that, daemon runs and you thought that it's actually launching the VM.
It helps to justify it.
So then if I open it I think you said
Second from the bottom is exactly revelation analysis on the
Yeah. So all Bluetooth app does is just gives you bash summary. And you got only host machine. So you thought that it's really on the VM. All the steps you did is on your host machine.
because I downloaded the recipes and I don't have the
official
Right.
by the author of the paper.
So
I think it's also show
on your machine, your host machine.
This is not
That's fine. I just go like this. I don't want to say this. So now I can. Now for the report and
Okay, so that's the purpose. So is that explained during the project?
I think it's not. It's so the dark difference is like and Mac. It's more calculus.
So the same sheet code cases.
Right, what should I do?
Nine in one case, not.
So run the book on that. And one's gonna come now.
So, okay, then I would follow, yeah, so this will build the engineer. And then, yeah, that would be one. So once it's built from this one, yeah. So this is what okay, and then so then that's before starting
no, again,
in the container.
no, you can do it.
Oh yeah, yeah. And then that one there and then when I log out of that, you want to do
So, well,
and all that, so all the containers
if they log in, well, it is, yeah, it's fine. It's like, you know,
I imagine that when the core file everything, which also means that they want to
yeah, I think, well, that's what we did with the Docker, remove RMI, like that, but so that virtual machine, remove all the stuff. So we
did a poll to get but this wasn't for the
I don't know, but we can find out. What do you like? This is what we end. Getting a new file. The new file system.
So that thing
I confess, I'm a
which also means if I get a new laptop without downloading the whole thing.
But I don't know where the file is.
I don't know how you ended up with
instead of doing the SSH,
but the point is that these are all remote I would remove all of these. Trying to get rid of that.
Yeah, I mean, it's a
Yeah.
Okay, welcome back. So let's do the final push of this exercise. So when we started this morning, we wanted to show you the entire process of going from acquiring a sample with the microscopes, taking images, sharing the images, writing an article, doing image processing on it, having the scripting of the process, and using DEXI in order to generate your scripted paper. So this is really the final stage, is to grab that PDF and share it in a journal that appreciates the concept of reproducibility. So this is a journal that we started in the ITK community about 7 years ago. And we changed the rules of the journal very on purpose because we were more interested on does the article works? And we don't care about novelty at all, because novelty is not part of the scientific method at all. That's a problem that publishers are getting very confused with the concept of novelty. So in this journal, what is required is that your articles have to include the source code and data and scripts and everything that is needed to replicate the article. That's the rule. And so this is really a scientific journal. This is what a scientific journal looks like. And it's about when you download the paper, do you get everything you need to replicate the work? And if you don't, then that's not a scientific paper. It's nice advertisement, it's nice marketing, but it's not an article. It's not a scientific article. So what we have done here is if you go to the insect-journal.org website, we have created a collection of issues. And on the right side, you will find that there is a SciPy reproducible issue. So what we're going to do now is that you are going to upload, you're going to submit your article to this issue. You may have already created your account, and if you haven't, then you can do that at this point. On the upper right side is the typical user registration. If you want to use a Google account, that's probably the simplest way to do it. So just logging into it. And then once you are logged in, you can select the issue where you are going to submit. And is the second one on the right side. SciPy reproducible. And you have this option of submitting publication in the upper right. Now the journal that you want to choose is this one, the first one at the top. So what it's showing you is that we have multiple issues open at the same time. So among the many rules, when you think about how publishing works, after a little bit of reflection, you realize that a lot of the restrictions that journals impose on you are due to the paper technology that they are still using. So the paper mindset, the physical paper mindset. So things like not being able to update a paper, an article, is because they're still thinking in physical paper as opposed to online publications. We don't print this at all, so we don't have any of the restrictions of physical printing. That means that issues are open continuously. You can always submit a revision of your paper. If you submit a paper 5 years ago and today you want to update it, you can submit an update. And you don't have to go through the entire publishing process. You just update your article. And if somebody finds an error in your article, you can fix it. So the notion is that the article is a real description of the work that you did. And if you have an improved version, you can submit it as many times as you want. All right, so you select the issue. And then there is the licensing. We haven't talked about licensing, but for all these things to work, open is a requirement. So we do open not because we are nice people, although we are nice people, but we really do open is because if you don't do open, you cannot replicate. Because access to the materials is a requirement. So for you to be able to replicate my work, you need access to the data, you need access to the code, you need access to the papers. So all of those have to come with licenses. The typical very easy solution to licensing on publications is to use the Creative Commons licenses. Probably the best suited one for this kind of process is the Creative Commons by attribution license. Please stay away from the non-commercial license. When people use non-commercial, they are thinking about not serving companies. The reality is that most non-for-profit organizations are commercial entities. So when you say not commercials, you're saying that universities cannot use your work. And typically means that you cannot use your own work. So it's very tempting, but it's confusing, and it's not very, it's not productive to do it that way. So you want to stick with the very open versions of the Creative Commons licenses. For documents, is Creative Commons by attribution. So you will get credit. Anybody can copy your work, but they will have to mention your name. So that's fair enough. And for data, you want to stick to the Creative Commons public domain dedication. It's called the CC0 license. Data is, by definition, not copyrightable, but collections of data are. So what you want to make clear is that you're putting your collection of data out there, and you really encourage people to use it. So that's all the story of what this license is here. So this is saying you are putting your work under the Creative Commons by attribution license. It also means that you retain copyright of your paper. How many of you have signed a copyright transfer agreement? How many of you read it? Okay, so you know what is in there. You know that you promise the publisher that if somebody sues the publisher for copyright infringement, you are going to pay for the legal expenses of the publisher going to court to defend themselves. How much did the publisher pay you for your article? So I guess that makes the point. So the modern publishing platforms let you retain copyright. Some universities are actually making the rule that you should retain copyright, and you just give a license to the publisher so they can publish your article, but you keep the ownership of it. Otherwise, as soon as you sign that copyright transfer agreement, that paper that used to be yours is no longer yours. Next time that you need to use anything from that paper, you have to go back to the publisher and ask for permission. And you have to ask nicely. All right, so this is a standard form to fill up. You will have your first name, last name, author. You can put multiple authors, the institution, an abstract, nothing special. And once you go through this process of filling up, the next click will ask you to, for the file, the PDF file that you need to upload. So at that point, you can put your Sandhopper article. So fill up this form. I will do one just for... You can put multiple keywords, as usual. If you want to have credit for grants, usually funding agencies appreciate this. So this is a good opportunity for you to make your program manager happy. It doesn't cost much, so it's nice to put your grant numbers here if you have any. And then you can just go to the next window. We need 2 keywords, OK. And essentially, the subsequent steps is going to ask you for a document, the PDF file. Then it's going to ask you for your code. And this is what is different about this type of journals. Other journals that are adopting this policy, a very important one is PLOS ONE, the Public Library of Science journal. They have adopted the policy that any article for which software is a substantial part of the work, the authors must supply the software under an open source license. So this is a very specific requirement, mostly in the biology space, but they are starting to understand that the code is required, that just the description of what you did as processing is not good enough. So this is going to ask us for the code. You could either upload the code in a zip file or a .gc file, or you can point to a Git repository. And this is what we're going to do. And when we ask you for the Git repository, we are going to give the address of the fork that you created in GitHub. So while this is loading, if you go to your GitHub forks, so this is our actual official repository, but I already forked it. So, oops. And it will send me there. Yep. So it will send me to the one that I already have. So this is my name and the fork of the repository. And then towards the right side, you will have this link here. You want to take this link, and you will use this same link, but instead of HTTPS, you will use Git, Git://. That's kind of the format that the journal is expecting. And then what the inside journal is going to do is going to go to GitHub and say, please give me a tar file of the most recent version of this repository. Now, there is an interesting movement. The same way that we did Figshare this morning, when you uploaded your image and you got a digital object identifier, that's the kind of thing that goes to your resume. Just it's another paper, it's another publication. So now there is this recognition among funding agencies, especially NIH and NSF, are recognizing that software matters. Big surprise. So for people who actually have software published out there, they are assigning digital object identifiers to your repositories. And GitHub did a great job of integrating this process. So you can go today and sign up. It's an additional service, but it's free, where you can sign up for getting digital object identifiers to specific releases of your software. So the way it will work is that you will go to your GitHub repository, make a release, and once you have the release, you can have it assign a digital object identifier that then you can put in your resume and say, I published this software. Now, you may be familiar with the notion that people prefer not to show their code until they publish a paper because they can be scooped and somebody's going to steal your ideas. It turns out that the best protection against that is actually pre-publishing. And publishing in an open environment is the best solution for that because now you have a reputable site that is going to give you a timestamp of when you publish this code and when you were doing this research. So you can always point back to that and say, I was doing this in 2012. And here is the proof. So pre-publishing is actually the best solution to being scooped instead of being afraid of sharing code and letting things flow. So that's a new environment. You publish your data, get a DOI for it, put it in your resume, publish your code, get a DOI for it, put it in your resume. And you can also cite those elements. So when you write your PDF paper, and you're running with DEXI, in your references, you can indicate that for this paper, you got this image that has this digital object identifier, and you use this digital object identifier source code to run the processing. So the elements of the recipe are getting together. They are uniquely identified. They are in places where you can get them back. And the next person who reads the paper and needs to replicate the work will find all the components. So here is just asking for a couple of, what are the areas of the paper? This is mostly paperwork. And here's where you will upload your paper. So I go to the temp directory where we have this Hopper paper that Anna just generated with DEXI. I certify that I have the right to distribute the file, so you should have the copyright for it. Upload it. And then next is going to ask me for the source code. So that's the signature of this type of journal. You have the article. Next, it will ask you for the source code. Next, it will ask you for the data. So it's happy with the PDF. So here you can, it's asking for the source code, so I can provide either a zip file or .gc file with the source code, or point to a Git repository. If I go for the Git repository, then I will have to write it here. So I go to GitHub, get it from there, paste it here, and just replace the HTTPS part with Git, and certify that you have the right to distribute it. Now, of course, that implies that you already put some open source license on your code. Please pick an open source license. Pick one that is well-known, well accepted. GPL, Apache, BSD. Just pick one. Don't write your own license. It's not worth it, the effort, and just confuse people. And then next after that is going to ask me for images. In our particular case, we could point to our fixture image or just upload the actual data set. Now, there is a back end to this journal where we actually, when we receive code that is with certain constraints, we actually run that code. So the first test on publication is that there's an automated system that is going to grab the source code, compile it, and run it. And we have the assumption that everything has been configured with CMake, a little bit along the lines of what JC showed you. So there is really this mindset. So if you're a software developer, we call this testing. If you're a scientist, we call this reproducible research, but it's really the same thing. It comes down to, can you do it again? And can anybody else do it again? So it comes down to just scripting everything in a very precise way. You give descriptions of whether your code will run in certain platforms. And here, because what we have is not the kind of environment that we could run directly in the back, here we are really expecting things that are written in C++ and with CMake configuration. Then we're going to skip the testing of the code. If we have not done that check, then the journal is going to actually try to run the code, and it's going to post the article with a first review that indicates how that compilation went. Now, I would ask you if you've seen any of these toolkits. Now, this happens because this particular journal was created for this community. So you may want to look at different journals for your communities that are adopting these policies. Or if you go to a journal, a mega journal like PLOS ONE, they really take from any discipline. They are really covering a large spectrum. Here you will load your data sets. We're going to just skip this. But normally I could have put the data sets there. And you can also put a decoration image for your article if you want. I'm going to pick this just for the sake of speed. And it gives you a last confirmation. So it tells you, you're about to submit this article. It has the source code, the PDF, the data. Do you want to do this? And then you finish your submission. And it will take you, it's going to take a few minutes. Now, the entire principle here is that publishing, we essentially skip the peer review process because it's broken and it doesn't work anyways. So what we do is that you grab your article, and instead of peer review, we have reproducibility. That is what the reviewers should have been doing, but they didn't the job the right way. So in this particular journal, when you submit, your article go online right away. There is no delay in the publication process. And it can go online right away because anybody who wants to verify your article will have the entire collection of materials to do it. And they will have also the access to review your article. So anybody can be a reviewer. This is what really peer review means, is that anybody like you will be able to review. So it's the principle of the Amazon market where anybody review, and reviewers also get rated. So you have the checks and balances. And there is no end to the review process. There is no end line for publication because that concept really belongs to the time where people was printing in physical paper that we don't do anymore. So this is the actual paper there, and if any one of you have submitted also, we will see all those other articles there. Now the final proof is, can you go to any one of these articles, click in the download the PDF. You can actually download all the materials. Let's proceed. Let me open this one in a separate tab. This is one that we submitted this morning. And what you will see is that in the download options, you could download just the PDF, or you can download the entire package. That is, the article, the source code, the data. And then you could, in your next step, verify the reproducibility of this work. And you should, in principle, report either positive results or negative results. That's another illustration of how broken the publishing system is that nobody publishes negative results. And negative results is really 90% of what we do, probably 99% of what we do. But this is not shared. So that's actually an obstruction on the progress of any field, is that those negative results are not shared. OK, so this is taking longer here. Any questions while we wait? So you may not have yet journals like this one in your domain. That's a hint that maybe it's an opportunity for creating such journals. When you think about what the IPython notebook is, combined with GitHub, it's really a publishing platform. So you could really skip the journal and use organizations in GitHub that has the rule that you should submit your repository that have the code and the full scripting of how to build an environment for it. That's equivalent to a publication. You have your code, your data, your equations. That's a full description of the work. All right, so if you wanted to replicate the work, you will have the download all button over here. And that will send you a zip file that has the PDF, the source code, and the data. And at that point, you should be ready to replicate the work. And you can go here right away and start writing reviews. Either you write the quick review of, say, thumbs up, thumbs down, or actually write a number of stars type of review, or go really in detail and write a couple of pages. You could also go and write an article that is the response to this article. And we embrace having articles that are 1 or 2 pages, because they actually go to the point. You don't have to prove that anything is new, because that's not part of the scientific method anyways. What you really need to demonstrate is what did you do, and to do in such a clear way that anybody else could do it again. All right, so that covers everything we wanted to share with you today. Matt, do you want to wrap up?
Thank you very much, Luis. And you're welcome to go and submit your results or your failed results or whatever you have to the special issue in the Inside Journal. But I wanted to thank everybody for coming out today. Hopefully you learned something, and it was a helpful experience. So if you have any questions, please feel free to contact any of us or communicate with your other participants on the Mozilla Moped or just in the SciPy mailing list. So.